Okay, good morning everyone and welcome back to another popular talk. Today's session will be conducted by Professor Jyothi Krishnan. Professor Krishnan got her B.Tech from NIT Calicut, MS from IIT Madras and a PhD from UC Berkeley. Having grown up enjoying puzzles, she was introduced to the world of modern board games during her PhD and realized that it is a way to make mathematical reasoning accessible to young students. With this goal, she ran a game lab for 4 years, playing mathematical games with children in alternative schools in Bangalore. Currently, she's an assistant professor at IIT Gandhinagar and a senior scientist at the Center for Creative Learning. Her session for today is titled Mathematical Games, where we will play and develop the mathematics of some games. Thank you.
Thank you. Yeah, okay, so I'm actually going to say most of that myself. So this is where I come from. This is IIT Gandhinagar. Some of the things you're going to see today, I've played with kids in school, and we're also using it to teach discrete math and other game. So there's a lot of mathematics, but hopefully it'll feel like 2 hours of play. If anything I say, especially the back, if you can't hear me, if you can't see my slides, please let me know. I don't want to be just talking to myself. So anything doesn't make sense, stop me, ask questions. Okay, this is just a game space for the next couple of hours. If you don't have, so at this point, all you really need is something to write on. So if you don't have a binder and a couple of pens, please let me know. So between the two, you need to find yourself a partner. If you're sitting next to someone, that's great. If not, maybe you want to move a little. You should have 2 different colors of marker. Ideally blue and red, because that's convention and I will be using blue and red. Okay, so are we? Yeah, okay, so then we can go back to how do I switch? Do I get the... Yeah, okay. So by the banks of the Sabarmati, it's kind of cheating because it's a dam that makes this river look so perpetually full of water. It's, yeah, anyway, it's a very pretty campus. Somewhere there is the lab. We do all sorts of stuff. We make, there's about 40 people at the lab, and some of us have PhDs, some of us didn't finish our 12th. It's like a very eclectic group of people. We like, with the exception of me, we like making stuff. I can't do much with my hands. But there's lots of interesting stuff that goes on. So if you want to hear more, we've got a lock maker in the lab who actually put together a replica Enigma machine, which I didn't bring it, it's too heavy, but it's functional. We make, fun stuff. This is something that we sent off to the Bridges conference this year. If you look at it from one side, it's Ramanujan. If you look at it from the other side, these are Rubik's Cubes, solved Rubik's Cubes. Look at it one way, it's one person. Look at it the other way, it's another person. So if you want to talk about the math of any of this, it's actually surprisingly a lot of math in much of these things. And then there's me. I was doing a PhD. I appalled my advisor by spending all my time playing games instead of doing... In my mind, I'm doing mathematics. But anyway, so lots and lots of games. And then I read Conway. So I read this excerpt. I think it's from one of the Winning Ways books. I'll talk about it. There's a lot of beautiful literature on games as mathematics. And there was this line that made me really happy. So what it says is, far from trivial, games are an enduring, essentially mathematical aspect of the human experience. There is much we can learn from them. And as Conway said, so Conway said he felt guilty. I mean, I guess this is all me assuaging my own guilt. But Conway says, and I'm not Conway, clearly. So Conway says he spent all day playing games while he was supposed to do mathematics, and then discovered the surreal numbers, which I will try to introduce a little bit today. And he realized that playing games is mathematics. Okay, so games are important because people play them, and combinatorial game theory has flowered because it's both serious and fun. Okay, so with all that, this one here is Conway. So we're going to talk a lot about Conway. So I thought I'd introduce you to some of the literature first. This is a 4-volume introduction to games. It's called Winning Ways for Your Mathematical Play. winning ways for your mathematical plays, and it's full of literature, alliteration, humor, and mathematics. So there are theorems interwoven between a lot of games. The author is a Camp Conway guy. And Martin Gardner, if you've never read Gardner's articles, I'd really encourage you to. It's a beautiful introduction to recreational mathematics. So Gardner was a journalist who spent 30 years writing popular articles on various forms of recreational mathematics, games, puzzles, things of other interest. You should really look it up. It's a 14-volume collection somewhere. Okay, so we're going to start by playing a game. So the way this works is, I don't know if I've handed out, I brought some buttons and then I realized I'm woefully underprepared. So we're going to play this by drawing it on so into this you can stick a plain piece of paper, or you could use one of the grids. Right? So the grids are going to be used for other stuff later, but don't write straight on it so that we can use it for other things. Put it into a folder. And then you should be able to write on it and erase, right? So we're going to start out by drawing heaps, piles of tokens, right? And if anybody would prefer not to erase, I have a few tokens, definitely not enough for all of you, apparently. Okay, so the way this game goes is there are piles of tokens, right? On your turn, you get to go over, pick one of these columns, and then take as many of the counters as you want, right? So the counters or tokens, there's 1 in the first column, 2 in the second, 3, 2, 1, right? You go over, you choose one of the columns. For example, supposing player 1 goes here and picks the top. It doesn't matter which counter, there's no directionality. There's just 3 in a column. Take any one you want. Take turns doing that. So player 2 goes over, takes those 2. Player 1 goes over, takes the first one. We keep playing until there's nothing left, and the person who takes the last one wins the game. Okay, so I'm going to ask you, what do you see about this game? I'm going to give you a couple of minutes to play, and then I'm going to ask you a few questions, and then we're going to try to turn it into some math. That's the plan for the first part of this. Okay, so do you notice anything? How many people are playing? Sorry, no, it's okay. So I know I said player 3 at some point, which is why I asked. It's 2 players taking turns, walking up to a pile of tokens, taking one, then the other person goes, keep playing back and forth until there's nothing left. Whoever gets to take the last move wins the game. Okay, so 2-player, turn-based. Can this go on forever? No, right? Because at some point we run out of tokens. Is it, what else? Is there any randomness? Okay, what's the randomness here? Oh, yeah, okay, so we'll talk about that. So I have a choice in terms of what I do, but still I could list out every choice, right? So it's still, there's no cards, there's no dice, there's no spinners, there's nothing. So I go, I make a choice, you respond to that choice. This is how the game proceeds. Okay, so I'm going to ask you to take 2 piles, okay, of any length. Just play with 2 separate columns with your neighbor and see whether you can figure out who wins. So if I see a board, right, can I figure out who wins the game? And we're right now working just with 2 columns. I'll give you, is there a clock in here? Yeah, all right, so 2 minutes. Okay, does anybody not, please somebody tell me you do not understand the game. Wonderful. Yes, Siva. You can take as many as you want from a single column. So the choice you have is pick a column, take any number of counters. So let's go back maybe. Okay, so the first thing you choose is which column you play on. Take as many as you want. Take as many from that column. Whoever takes the last one wins the game. So right now, I'm going to ask you to set up 2 piles, okay? It's not my pile and your pile. It's 2 piles on the table. Each of you has the same choices, okay? But let's start by playing simple. Let's just set up as many coins. You two decide. Yeah. Okay, there's no, I can't do an overhead kind of thing here, can I? I could do it on the board. Okay, so maybe one way to do this is, how about you all play against me once? If I can find chalk, I'm going to set up. So what I'm asking you to do is to just have two piles. What's your name? Okay, so Kartika and I are going to play a game. Kartika, you can go first. What would you like to do? She's choosing the second column and she wants to take one of them off of here. Now I have to, okay, so I don't want to play because I'm going to be, what's your name? Yakshita, would you play next? Yeah, so what would you like to do? You can, yeah, it's just a bunch of coins. It does not matter that I've put them in a line. You're going to take this one off of here. So it's back to you. What would you like to do? I was playing with you. This top one? All right. Yeah, so what do you want to do? Whatever you do, she's going to win. Wonderful. So we're going to try to see if we can generalize that idea. So go ahead, make any number of, just make 2 columns, 2 minutes. So there's a question, and I'm going to, are you comfortable asking it out loud? I'm sure there are other people with the same question.
We have to, it's our wish, then we can take any of the columns.
Yeah, so you start by choosing one of the columns and take as many from that column as you want. Ideally, start with just 2 columns so that we can see something about it. As in? Yeah, sure. Right, so I would say just use 2 for now. Yeah. And it doesn't matter. So right now you're, I think, so that's one of the things.
If you says that the one who takes the last
Wins the game. Yeah. So the one who takes the last token counter wins the game. Okay. So if anyone wants to volunteer, yeah.
if two tokens are left.
Any number from one column of your choice. After you've played around, can you give me any logic of who's going to win? So for an M pile and an N pile.
Okay,
Yeah.
for this thing, if we choose this thing,
Think. Does anyone want to volunteer any observations? Yeah, you do? Do you want to volunteer any observations?
The first person who is starting this game, he or she will always win if 1-1 is played.
Ah, okay. So the claim is that if there are 2 piles, the first person who starts will win if they choose to remove just one pile, just one off of a pile. Okay, so let's see if we can disprove that. The first person will win. All right. Sorry, I didn't ask your name. Okay, so I will set up this board and ask you to start. So your claim is the first person will win by removing a single token. Sure, I promise to remove only one. Go ahead. Yeah, go ahead. Which one do you want to? So which column? Would you like to pick this column or this column? Either one? The one? This one? And you want to take one off of it? You want? All right. Okay. There are 6. Yeah. Correct. Very nice. But and if you do 2 and I can do only 1, that's kind of a cheating game, right? So, so Okay, so let me ask you to make that a little tighter. So, so you're saying that it depends. I'm not putting any condition on how many you can remove. I'm asking you, can you characterize the pile based on how many I put in each column? So if I have two columns, one has m tokens, one has n tokens. Can you tell me anything about m and n? Okay, yeah.
If M is equal to N,
Yeah.
player 2 wins. Otherwise, player 1 wins.
Perfect. So the claim here is now is that, okay, can you tell me what's the strategy? What should I try to do? And I'm going to try to generalize. So now we're saying that if M, okay, then first player wins. Huh? So first player loses, right? So second player wins. I mean, okay, so what I'm also going to ask you to do is, when you walk up to a board, does it matter if you were first player or second player? Does it? No, okay, so we'll talk about that in a minute then. Leave that out. So, who was I talking to? Sorry, name?
I'm Larissa.
Okay.
So if m is equal to n,
Yeah.
and the first player removes, suppose, k tokens from any one of the piles, the second player's strategy should be to make both of the piles equal again.
Wonderful. Okay, so I don't know if this makes sense. Hopefully, as we go along, we will do this so often that if I wake you up at night, you'll tell me this. But so what she says is, take any number, take k off of pile 1. The response should be to mirror it. Take the same amount from the second pile. Yeah? And if it's not, if you get to play and you see two unequal piles, equalize them. Equalize them, give them to your opponent. There's nothing they'll be able to do. Okay? So hopefully then, let's just run through this a little. Okay, so the things I want you to notice is this is a 2-player, deterministic, finite, impartial, no draw. So either someone's going to win. There's no way to have, so someone's going to win this game. So we can do this more carefully if we want to later. And it's what's called normal play, which means that whoever makes the last move wins the game. Okay, so this is what we just did. I want you to contrast this, but we're going to play another game. All right, one more game, which I'm going to actually experiment by teaching. Okay. So in this game, I meant to play a few levels. I forgot. Okay, so now we're going to change the game a little bit. What's going to happen now is there's going to be some picture in front of you. Now the color of your pen matters. One of you is a blue player, one of you is a red player. Does internet here works, right? Yeah, okay. So as we learn this game, all of you are red and the computer is blue. All right? Now what you do is you get to cut off, erase a line of your color. So if you're red, you can only erase red. If you're blue, you can only erase blue. Who wins this game? Okay, so we're starting as red. What should we do? Okay, so I'm hearing, so there are only two options. Either red can cut that or red can cut that. Votes for this. Does anybody want me to cut this? Nope, so we collectively want to cut that? Yeah, all right, let's do it. So, okay, so this is kind of, okay, not that it makes any difference, but we're going to do just one more of these to make sure. So is someone unclear on the rules? I would like, yes, wonderful, play with me. So you're red, you get to choose. So your option is to walk over to this and erase or cut one of the red branches, one of the red sticks. Pick a stick, and I will cut it for you. So your options are stick right on top of the left branch, at the bottom of this branch, or the one up here. Which one would you like to cut? Always to make the last move. So it does not matter what you see in front of you for the next hour or so until I do a different kind of puzzle. It's going to be make the last move is your goal. What do you want to cut? The one on the left, do you want to cut at the bottom or do you want to cut on top? At the bottom? All right, let's do that. Okay. Now, unfortunately for us, the computer responds by cutting right to the bottom. So let's look at that once more. Okay, I can hear a lot of murmuring. Okay, talk to me. So we should cut. I had a mic that I was brandishing, and then I don't know what I did with it. Yeah. Apparently Asta tells me that in my wisdom, I forgot to tell you the most critical rule, that if you cut at the bottom, so the gravity, so earlier we didn't care if there were gaps. Thank you, and I have major apologies. So earlier, it didn't matter if there were gaps. There was no notion of things falling down. Hackenbush, this game is called Hackenbush, and it's a very big deal, and hopefully by the end of this, we'll know a little bit of why. But if you cut anything, and if it's not connected to the ground, it falls. Okay? So yes, I think I smartly started with one where it didn't matter. But okay, so now do you want to play again? Obviously, you didn't understand the game because I didn't teach you the rules. So now that we do know the rules, so you cut anything above it vanishes. You want to cut the left, you want to cut down here? So okay, let's think it through. If we cut here, if I were the computer, I'd cut there, and it's over. Okay, let's do that. Yeah, I can hear some, even if we cut, we'll talk about, all right, it did something, and then we have only one choice, and it's a good choice for us. Okay, so again, so what's happening is cut a branch of your color, anything that's no longer connected to the ground falls down and is lost. We do one last one, and then maybe we think about one last one. These are all the same thing. I should have played a few on your computer. All right, the same old, isn't it at this point? So, okay, tell me what to do. The middle one right at the bottom. Okay, instead of letting the computer play this out, shall we do this one on the board? So let's get two, do we want to split the room down the middle? I guess it's hard with such a large group, right? So I had one volunteer player somewhere here, who I've now lost. Was it you? Yes, wonderful. I think, tell me your name, not that I'm going to keep all this in my head. Sangeeta? Okay. Somebody from that half of the board? Wonderful. One half, that half, yeah, okay. So Asta's playing.
No, I'm not playing, I'm just making.
Asta's making me things, apparently. I was looking for something vaguely reddish. We could do this. Okay, so while Asta draws that, yeah. Okay, so again, okay, let's give her a minute. Can you see at the back? Yeah, what she's drawing on the board? And its color. Okay, wonderful. Yeah. And then a single blue stick. And I mean, you didn't have to make it so beautiful because off it goes in a minute. All right, so Sangeeta, what were you doing? Yeah, start as red. Yeah, actually, why don't you come to the board instead of us having us? Somebody here volunteered? Yeah, please. Okay, so what you do is you erase that branch and anything that's above it. So we needed a ground. So maybe let's have a ground. Okay. Yep. No, it's, yeah. Okay. Do we see anything? Did you notice anything? So as you were playing, was there anything you were trying to do, or was it just, let's look at a branch and see which one we can cut?
No, we should let arm would be the last. So I had a blue on the right hand side. So I would want to save it for the last blue.
Ah, okay. So right now what we're saying is this blue, no one can mess with. This blue is blues no matter what red may do. These are the two that are a little more we need to think a little bit about. So when you were playing as red, how did you pick? In a minute, we will actually be able to do this mathematically, but instinctively. Ah, okay. So she says, what if I were to try to equalize? Well, now these two would be equal, but not that. Right? So maybe it is true that this board is not an even board. This is a winning board for red. Okay, so it's okay. So let's do this a little bit more. Let's switch back to the PowerPoint for a minute then. Yeah.
I had a doubt.
Yeah, wonderful.
Like, what if it's the red player's chance, but there's no red stick over there?
Perfect. Supposing you walk up to a board and it has only a blue stick, you've lost already. Okay, so you can only make a move if there is a branch of your color somewhere that you can cut. No, no. So I'm going to draw some more interesting stuff. And okay, so now the difference between the game that you saw before and the game that you're seeing now is that this one is what's called Partisan. So the moves that one player has are not the same as the moves the other player has. You're playing as blue and red. Earlier, it didn't matter. You walked over, you took some coins. Didn't matter, right? But other than that, very similar. Okay, so now somebody talked to me about how there are several options, right? So here's a tiny little board. Supposing red, I can't remember what I did, blue to start. Okay, so how many choices does blue have? 2. Now let's see what happens after that. Now, what happens to the left position? Anything, have we noticed anything about the one on the left?
Blue wins.
If blue is able to give red that board, blue would win the game. Wonderful. In the other case, so what I'm going to try to do is that's what you guys said. So to anyone, so red would have only one choice to cut their branch, taking it to nothing. There is another path in which red would win, but in combinatorial game theory, you're going to assume that people play in their best interest. Okay, so there is no taking paths which are suboptimal for you. So this part of this tree would never happen, and we assume always that blue takes their more favorable path. So there's one way for blue to cut the last branch and win the game. What if red started? So unlike NIM, so when we talked about NIM, we said first player, second player, this player, that player. Here it is who starts and what color you play. So 2 things that matter now. Okay, so what if red starts? Again, you'll find that there is a way for blue to win. Okay, so I'm going to take away. So red would never take their dotted path because they lose at once. There is some path to victory for blue on the thing that I drew. Okay, so, and now, I asked if you walk over to a board and you played it. So, well, what we're going to say is you don't know where these games came from. Each one of these can be viewed as a game in its own right. Right? So, every game, after you play around, is a game itself. All right, why does all of this matter? So, hopefully in a minute. Okay, so we've said this. Is this winnable? If you saw this board, would you be happy or would you be like, I don't want to do this? Okay. Okay, so I'm going to assign to this a value of 0. So now let's start trying to do some math on this thing. Okay, last of the who wins things. Who wins this board? So second player to win. So this is actually, even though, so this is from the book, even though it looks like this, it's really the same as having a blue stick and a red stick. What about this one? It's the same thing. I've just taken a few and moved them around. It's still for any move you have on Tweedledee, I have the same move on Tweedledum. Right? So for every move on the guy on the left, there is a matching move on the right. All right? So this 2 then is what I'm calling a 0. If the blue player has one extra move, that's the thing that I call a 1. And I'm putting the dot on here to say that this is a game, right? So the dot 1 to mean this is a game with a value of 1. I don't know yet whether it's just a number. Okay, so dot 1 is just like 1. And if red wins, I'm going to say those games are negative, and I'm going to call them -1. So either blue wins or red wins, or it's a balanced game, which means whoever goes up to it, if they play, they lose. Okay, so now, can I do addition on this system? So if I did addition on just numbers, I don't know why I want to stop here. You can all add -2 and 3. What about if these were games? How would -2 look? 2 red branches, 2 red on the ground next to each other, and blue would be 3 blue on the ground next to each other. So something like this. Addition is just put them together and play. In this universe, to add is just to play all of this all together. And you end up with a single blue stick. Okay, so essentially this is a system in which I have addition, associativity. Doesn't matter in which order I decide to combine them. Combination, you combine these games, it's still one large game. I know you're probably not, you're all in your first year, so I don't know if any of this is going to have any aha. Does anyone recognize the structure? Yeah, exactly. So I can do, how do I negate this? So this is some value, I don't know the value, I don't know how to assign a number to it yet. But whatever it is, can I find its inverse element? Yes. I take every blue branch and turn it red, right? So no matter what number it is, there's a minus alpha. Okay, it doesn't matter whether I stack them or I put them side by side if they are the same color. But what about this? Okay, here's where you take a couple of minutes. Think about this. Who wins this game? Very nice. No matter. Doesn't matter whether, what if blue started? It'll take the top branch. If red started, it would all be over. They would just start by chopping the bottom. So is this a positive game or a negative game in our new language? Negative. It's a negative game. Wonderful. Can I assign a value to it? So now I've bounded it. I've said whatever it may be, it's less than 0. Okay? Strictly less than 0. It's not a 0. Do I have anything else I can compare it to? So I know it's negative. If I wanted to balance it, so I try to pull it back towards 0, what if I played this game next to a blue branch? Who would then win? If I put... Does anybody think red would win? Can we try that out? So the thing is, if I put a blue branch next to this, so I've got something sitting on top of another thing, and now we say blue wins. Yeah, so again, we've said if there is a better play for blue, play must not take it. So this branch of blues, which I have, I don't know why. This is where we are. So you're saying chop that, right? But what I want to always try to do is give my opponent one blue and one red, right? So what I would prefer to do is to take that one on the top, okay? Giving the other person a 0. So what I've got, where I've got right now is this is somewhere between -1 and 0. Okay, so I know that it's +1 was not enough to get it balanced, right? So it was less. Okay, so can somebody talk to me? I can see some confused faces. So I know we're doing a lot. So I would really like to know. I hear some answers, I respond to them. So I would like someone to slow me down and ask me a question. Yeah. Correct, correct, correct. See, exactly. So each player chooses at that moment, the most optimal move they can make and makes it. Under that condition, there will be someone who wins. It's not basically, there's a theorem that says that you can either, the first player will either draw or win, and the second player can at best draw in games of this sort. This game doesn't admit a draw, and it's partisan, so it's okay. Strike that. Essentially, I'm taking draws off the table. So I'm saying that the options are either player, I mean, I don't want to call them player 1 or player 2 because, like we said, when we walk down the tree, each one is a game and the person playing it could be different. So any game board, someone has a path to victory. And we're trying to, if it is blue who has a path to victory, we're calling those games positive. If it is red who has a path to victory, and that path is despite the other person's best play. Right? So if you can win as red, you can win as red no matter what blue may do. The claim I'm making is that this one, blue can win no matter what red does. Poor red only has one choice in this game. So it's a. So the equation I've managed to set up, and we're going to pause and do something. Okay. So maybe, yeah, somebody had a question? Yeah. I should not have showed that.
इसमें can we conclude कि if I want to see the lowermost sticks, so the number of sticks which the color which has more number of sticks at the bottom
Very
will
nice, very nice. Well, okay, so win is strong, that it is powerful to have sticks close to the ground is a claim we can make. That you will win will depend on what the other person has in terms of sticks close to the ground. So all I wanted to establish at this point is this is different from just having a red stick. It's not as great as having a red stick, but it's somewhat better then, so essentially we've bounded it. We've said it's somewhere between -1 and 0. And all the information we have right now is these integer positions. Can we make this bound closer? I accidentally showed the next slide. So, no, okay. So you've seen games in which there are 4, okay. Right, so let me take that in 2 parts. One is what is the difference between a -4 and a -1, right? So, okay. So what we're saying is a win for blue is positive and a win for red is negative. Now we are trying to assign meaning to the number part of this. So essentially, if I had 4 blue sticks, that's like it's 4 moves for blue. So which is why you've got these game sheets in front of you, because the value of a game matters when you play it with another game. All right, so what we're going to do in this, if we have time, we'll play it as a tournament, we'll see, is you pick a game and you make a move. So if you see a game in which you have 4 moves, that is better for you than a game in which you only have 1. So so the number tells you how many moves. So 4 red sticks is potentially 4 moves for red. Okay? Does that make sense? Yeah, no, not really.
Maybe also you can tell what was 0 again, like.
Okay, so there are many ways to see the 0. You could see it as a +1, -1. So let's go back and look at the thing I've been calling 0. Okay, this is what we call 0. That's a +1, that's a -1. We know we have addition, together they're 0. That's one way to see it. The other way to see it is balanced in the sense of there's no clear winner. What you don't want is to have to play. Whoever plays this board is going to lose. Okay, so I saw one more hand up, but I lost that hand. Okay. Yeah? All right, so let's go back. How can I do better? Can I make this bound with only the information I currently have? Can I make this bound narrower? Okay, I don't know how to do pretty much anything. All I know how to do, so I've got some things I've assigned integer values to. I would like to assign some number to this thing. Okay, maybe this is one that you should play. Take a couple of minutes, play it, see if you can figure out. Okay, so clearly this is not an integer, right? So I've put it it's between somewhere between -1 and 0. What is it? Okay, so we've got an associative closed operation, addition, which means, yeah, sorry. Okay, so the bound, what I've done up to here, I think is not quite clear. So let's go back a little bit. What we did is that this is a game. Hold on just a second. This is a game that's different from what we called a 0. It's different from having one blue stick next to a red stick, because no matter who starts, who wins? Are we clear on that? What we've said is victory for red is what we're calling negative. So are we in agreement that this is not a 0 and it is strictly less than 0? All right. Now the question is how much less than 0? So what we could do is we could see whether putting a +1 next to it, adding a +1 to this, does that balance my system? Does it bring it to 0? So it does? It does? Okay. Yeah. So what does that mean? Sorry, let me just go to this. That means play this game next to a blue stick and ask yourself who now wins this game. Yeah, so go ahead, do it, and you've done it. So okay, so shush then, let me come there. Coming. Okay, what we've established is a win for blue means whoever starts and they do their very, very best, blue still wins. think consistently what's confusing people is, let's just do this little piece once more. So this we said red wins no matter what. Red win is negative. So hence this is less than 0. It is also not a 0 because red is winning. If it were a 0, then we wouldn't be able to tell who wins. Whoever plays first loses. All right. So then we said, all right, let's stick a blue stick in. When we played this total game, no matter who may start, and I encourage you to check, blue will always win. Blue winning is positive. So now we're saying that whatever that x is, add 1 to it, and now it's positive. So x plus 1 is greater than 0. X is greater than minus 1, but it was less than 0. So it's somewhere between minus 1 and 0. Yes? Yeah? People want to put a red stick on top of the blue stick. Wonderful, yes, that will work, but now I won't know the value of either. I will know I have an x and I have a minus x. I will be none the wiser, right? So yes, it is very true that I add them, I get 0. Yeah. Sorry? I'll pick it up for you, just give me a minute. You have a mic, use it. Yeah. I'm sure other people have the question, so ask it loud.
Why don't we draw the 2x, identify 2x plus 1?
Very good, go ahead, do it.
That is
Shush, shush, if you've got a value, wonderful. Keep it to yourself for a minute. Uh-huh. Yeah. Agreed. Okay. Because if x So we are not counting sticks. Someone is asking me, can I count the sticks and say this is the value of this game? The answer to that is no. Because what we've said is an extra move. A blue 1 on the ground is a +1. A red 1 on the ground is a -1. Anything else we know nothing about. This is all the information we currently have.
On the ground.
Yeah. Sticks.
Hello.
Or you can add a couple of
A
unknowns.
zero game is कि जो पहले चले whosoever starts first will lose for sure. Okay, a zero game, a value, a game जिसमें ये decided है whosoever starts first will lose for sure is a zero game. So you can try to use this property to find the value of x, to make it turn into a game that you make it that whosoever starts first loses for sure.
had given me a value. Could you put your hands up so I can give you something else to do? I can't remember who it was. Somebody up here. Some of you had found a value. I don't want you to sit doing nothing. So if you're doing something, okay, so solve this one. This is a, what's that? Yeah, there was one more somewhere here. We'll give it another 5 minutes and then I'll talk us through this. Someone here had given a value. I don't remember. Yes, but some. Ah, aha. Okay, so I think one more point of clarification. So what you're trying to do is put something together that is totally a zero so that you can figure out what x is. So I'm getting a lot of, but what is x? We don't know. We're working with hardly any information. We're trying to figure out what x must be. It is a game. We believe it must have a value. What is that value? Yeah. Ordering is a little bit unclear. So if I put two of these things next to each other, I am making red's power, red's benefit even stronger, right? So two of these X's, I totally can do that. I can put two of these games together and play them, but it's even better for red if I do that. Okay, and then to the question of what does balance mean, it means can I add something in to try to make the whole thing zero? And I think maybe we should. So I think we've got, so let's quickly walk through this. I think, okay, so I don't know. Okay, if I have left the pointer at your table, would you let me know? Yeah, wonderful, thanks. Yeah, okay, so I think now I've got a, all right. So again, we bounded it. We said, well, adding another. So we have a few options here. We could add another branch on the ground. But this thing is associative. Anything I add there, I'm going to add to this one. Not really going to help me much. So what I can do, as many of you have figured out, is play two of these games against one of these. And it turns out, hopefully you've tried it, whoever starts this combined game is going to lose. So this whole thing is a 0. The value I assign to this is a minus half. Okay, so now, okay, so I've asked some of you this. Does this become, so what am I doing? I'm pushing, yeah. Yeah, okay. All right, so now the advantage is moving redward, but maybe not all the way. If I put a red branch next to this, what would happen? That red branch would be really powerful. Yeah? Okay, so how do I want to do this? I'm very, very tempted to make you, okay, I'm going to walk through this and give you the slightly, so if I play two of these off against a half, I will be able to balance it, figuring out that that is a 1/4. So I'm going to ask you to tell me what this thing is. I've got a blue branch on the ground, K red branches on top of it. What's this thing? Huh? One, yeah, you're right, go ahead. Right. Okay, so this, I said I should not have done this. The blue is on the bottom. I switched colors midway. So blue is on the bottom, all the reds are on top. So this is a plus 1/2k. What if I have alternating branches? I don't want you to do this. I have more interesting things I want you to do. Let me walk you through this. So essentially, there are going to be ways to construct all the rationals out of stuff like this. Change the colors, keep playing with it. But I don't want to do any of this. What I want to do is introduce you to what makes this theory so... Okay, the other way to have done this, instead of doing it as a... you could have just played it as a game. You could have figured this out by a process of trial and error, I guess. Okay, so here's the question. Are all Hackenbush positions rationals? I'm going to leave that one open and introduce you to this. Okay, so till now, we had what are called partisan games. Red could only play red, blue could only play blue. I'm going to introduce a new color. If I have green branches, anyone can cut them. Okay, so blue can cut this, red can cut this. What is this game? Is it a 0? No, because I said a 0 means if you play, you lose. You play this, you don't lose. You win. So it's not a 0. Okay. What's its value? So let's compare it to something. Okay. What if I put a blue next to it? Who wins? So anyone can cut the green branch. Whoever starts cuts the green branch. Only blue has a move left. So no matter what happens, blue wins. But I'll ask some more. Can you tell me if I put this thing next to it? Can you quickly argue for me? So what I'm doing is I'm putting a green branch next to this. Who wins? Because just play it. I mean, just play it. Blue. So I found. What if I flipped the color? Okay. So it's okay. It's a little bit difficult for me because I don't know this group very well, and I don't know if I'm not making sense to anyone. So you have to stop me and ask because I really like being asked. Okay. So if not for you, for me, if this is not clear, can you help me out and tell me why? Okay, so the question I'm asking is if I took this tiny, tiny little thing, this is 1 over 2k, and I put a green branch next to it, who wins the game? I heard a red. Can the person who said red talk to me, please? Okay, so let's talk about red. So there's a green branch on here. And who wants to start? Do you want to be red or blue? You want to be red. So you cut maybe one of your red branches. Yeah? I start by cutting the green branch. I as blue. Yeah. And then you can do whatever you want above. I'll cut the bottom. So now what I've managed to figure out is that whatever this object is, it's somewhere between this very, very small positive number and this very, very small negative number, and yet it's not 0. So these things, so what I'm showing you is the beginning of, so what Conway figures out is there's a whole number system, he calls them, Knut actually names them the surreal numbers. So I'm introducing you to numbers that are not the reals. I could have used Hackenbush positions to make all the irrationals. I will leave that to you to play with. So you can get all the reals out of red-blue Hackenbush. As soon as I add this new branch in, I start creating new numbers. So what is this thing? So it's something that we say it's confused with 0. So whatever it is, it's not quite 0, but it's not very big either. All right? What happens if I play 2 of them? Which is what? Which is a 0. So if I add 2 of these things, and if I tell you the name, have you seen this before today? I mean, not in the distant past, but today, does this look like anything familiar? It's more like one red, one blue is still something that only, so this game we called, so things like this, we set up Partisan. Red can only do red things, blue can only do blue things. Greens are what? They're like a game we started out by playing today. They're impartial, it doesn't matter. Whoever wants to play them can. Turns out the mathematics of this, okay, so what I'm going to say is that this is really nim. So what you were doing at the beginning of this was actually playing green Hackenbush. I would actually like to show you the mathematics of this, but I think we've done a little bit too much math. So what I think we want to do is take a break and solve a puzzle. Okay, so give me a second. Let's use the stuff we learned in Hackenbush. And I'm actually going to hand out stuff and let you take a small break from this. I don't know how to make it full screen. Why not? Nah. Okay, I will figure that out in a minute while you do stuff. I'm going to make sure that, okay, so I want all of you to have a couple of nails. Okay, so each of you take 2 pass. Okay, I'm going to take a few out here. Each of you take 2 and pass. All right. Okay. So again, take one and pass. Each of you, if you want to solve independently, if you want to work with someone, I think I have enough for everyone. So take one, pass. And I need you to have pictures. Okay, wonderful. Take one of these as well and pass. Okay, so once you're done with all this passing, you should have two nails, a photo, a picture frame.
Sorry, one each?
One each.
It's clear to me pair.
Oh, well, if you would be happier working with someone, you're very welcome to. I think I have enough for you to work individually. So it is your choice whether you want to work in a group or not. Take one. Wait. Yeah, go ahead. Okay, so I'll give you a minute to do that. Yeah. Yeah.
You said Yale is the green Hackenbush.
Assumed I'd have an overhead thingy. So this is going to be a little interesting, but we'll work it out. Okay.
Everyone has got this thing.
You only need one each.
These are the extra ones.
Things in this picture. So two nails, something to hang it on a wall. The rope in the picture are already pre-assembled to save us some time. So you should have a photo on a thread. What are you looking?
The nail box.
It's back in the front. So, okay, so does everyone have one of these? Yeah? The last. Does anyone not have picture frames? Okay. Here you go. Okay, so you don't have the Eva. That's the thing I did not bring. Why don't you come down with me? Yeah. So back up here, maybe if you're missing something, you can come with me. You have extras. Do you have? Here you go. Oh, if you're working separately, you need one. Then you just need one. You need the Eva here. Okay. So, picture frame also here.
No, not this thing.
Yeah, so these I've not handed out. I don't know how to. What happened is I thought I would do this on an overhead and I don't know how to do it now, but I will figure it out. Okay.
Maybe you can have like I can write big
No, I'll write it on the board. Okay, so let me tell you what you're trying to do. So, oh no. Okay. Yeah. The photo frame? Yeah. Okay. So the puzzle is the following. Um, okay. So the way you regularly hang up a picture, if I were to take off one of the nails, what would happen? I mean, no, this is not math. I'll say anything. It'll tilt. I couldn't care less. My system, I care if it's hanging or on the ground. So it's still up, hanging off one of the nails. We call them nail A, nail B, whatever. The puzzle is the following. Can you hang this picture up on these two nails so that I can pull it, it's nice, it's stable, but if I remove any one of the nails, it falls down. Okay? So I want to, I gave away all my nails. Okay, can I borrow your frame for a minute? Okay, so, yeah. I don't know if you can see at the back. Maybe if you can't see for a minute, you need one of this. Yes, for sure. Yeah. Okay, so here's my question. So I do this, I take it out, it's still hanging. What I want to do is to try to do some sort of a winding. So that, and I hope I haven't messed up. So it's nice and stable, no cheating here. All right. But if I pull one out, oops, sorry, 1 second. Maybe I should put a finger on it. Again, I hope this works. So I take this out and I pull it and off it comes. Okay? So I have, it's not cheating, it's just maths, all right? No magic tricks here. So what I'm doing is, I'm going to do, okay? And it doesn't matter. Do you want me to, it's nice, it's stable. Hold on, it's nice, it's stable till it has to hang over both the nails, right? So it doesn't matter what you do below the nail. My operations are all involved going over the nail, right? And I go, sorry, what? Okay. Okay. So you want me to, which one do you want me to pull off? This one, all right. So hold on to this. So it's not falling off yet. I take this off and I pull it and it comes off. And it's symmetric. I can do that with either nail. Okay. Did you know how to get hold of the either one of the nails makes a picture. Hanging on both nails, a picture is nice and stable. Remove either one of the nails and the picture comes. Yeah, either one of the nails. Yeah. Yeah. See, sometimes what happens is it bounces and then it messes up your math. So take it out. And then let's see. So never mind. But no, it's still hanging on. Huh.
Both the pins you remove.
No. If you remove both pins, of course it will fall down. You pick either one.
Even if they
You remove A, it falls down. You remove B, it falls down.
For both of them, if you remove one at a time, it falls down.
So if I do this one, remove green, it will fall down. But if I remove A, it won't. Yeah. So I don't know. This is not quite a solution. I get to pick. I will walk over to your solution, choose a nail and pull it out. No matter what I do, it should fall down. So it should be, yeah. Now you don't get. Okay. Yeah, take it out. Very nice. Yeah, okay. So it will come. Wonderful. And I think it was symmetric. Okay. Are you allowed to keep on winding? Yeah, definitely. You do what you want at this stage. Huh. So you're asking, should I go over a nail more than once? Yes, definitely. Yeah. Okay. So if you've done that, do you want to? Okay, I want to turn this into a representative. I want to be able to. Okay. So what if I? So people who've done that, let me give you 3 nail puzzle. All right. Who's done it? Who am I giving to? Okay. 3 nails. Huh? Ah.
Said, like, I may not be allowed, he said, right? So I just went round and round and round.
But round and round and round may not really help you. Let's see.
Smudge this way. At one point, it got smudged.
So it's like using the friction.
No. We're mathematicians. No friction. Yes, we have gravity because we get to pick, but no friction. Thank you. Okay, so maybe one thing that might help is maybe if I define some operations, life will be a little easier. Yeah. Bounce off nails are not solutions, right? So what you should be able to do, you should hold the other nail in, remove the nail, and then when you tug it, it should come off. Right? So I've seen versions in which it bounces off because the force with which you yanked one, that's not okay. Right. I think you were close. Okay. Yep, that looks right. Yep. That may have just jumped. But I don't know if it just jumped because I had my hand on it. So I think not quite. But getting close. Yeah. Okay. Yep. You're really close. Now, okay, go ahead.
Yeah, and then if I hold this out,
Yeah.
then this essentially has nothing to add.
Exactly correct. Exactly correct. Yes.
Both sides.
Okay, so maybe this is why a little bit of, maybe we need to set up some rules of this game. Okay, so this is just a problem. Okay, so I don't know. So I stole this from I should probably have pulled up my slides. Anyway, it doesn't matter. Okay, let me tell you this. So what I'm going to do is I'm going to try to make this something I can write out, right? Because it's really hard for me to imagine this as a physical object. So what I'm saying is I'm going to move the front of the wire. When I move clockwise over a nail, I'm going to call that operation A. If I go clockwise over the other nail, so again, choosing one end, I'm going to wind it. If I go over a nail, that's an A. If I go over the second nail, I'm going to call that a B. If I go anti-clockwise over a nail, I'm going to call that B bar. And if I go anti-clockwise over nail A, I'm going to call that A bar. Right? So the problem now reduces to if I remove all the A's, I want the B's to come together and smush out. If I remove all the, what did I just say? Whatever I said, the other one. If you remove the A's, the B's come together and okay, so imagine what happens if I go clockwise and anti-clockwise. So I have a wire, it goes like this, and then I wind it back. That effectively does nothing, right? So if I were to yank this, it would just fall off, right? Now what I want, I definitely do not want, so let's leave that there. If I were to go wind over here and come back, well, the first time I yank it would come off, right? So in my representation, what is this? This is just A bar. What's this? Well, first I went over A and then over B. And then I came back over the B. Right? But this is bad news too. Because these two cancel each other out. And then so does that. So when I yank it, it all comes down. Okay, so, okay, in my opinion, I've given a big hint. So if that doesn't help at all, let me know. So you want to write something or use the things, there's pieces of paper that Asta must have given you, rearrange them so that so removing a nail is equivalent to removing both the A and the A bar. Yeah? So try to set up your A's and A bars so that if you, together they don't cancel each other out. But if I take one out, the other ones do. Yeah. And okay, so one moment, let me just do one thing because I have seen some solutions. Yeah, hold on, I'm coming, just a second. I'm not going to set up. I guess for those of us who have worked our way through that, move on to 3. Okay, who had a hand up? Yeah. Yeah. So if you work with the whole loop, right, it's a little bit hard to see what you're doing. So I would recommend that you take a hold of your picture, take one of its ends and work with that. Okay, so don't take the pair of strings and do it. Work with one of the wires. Okay, so to those of you who told me that the Hackenbush game was a group, and if you don't know what a group is, don't worry, you'll know within the course of the next semester probably. But was it commutative? So I mean, all of you know what commutative is. So with Hackenbush, did it, so I mean, did it matter if I did A plus B, right? So some game A and then added B, or some game B and then added A? Did it make any difference? No? So that was commutative. This puzzle that you're doing has all the same properties. There's an identity. The identity means nothing is over the nails. There's an inverse. Go clockwise, go back anti-clockwise. It's closed. No matter what you do, it's a picture hanging puzzle is a picture hanging puzzle. But it's not commutative. So the trick that you're trying to use is to use the non-commutativity to solve this. Okay? Yeah. Sorry, you have. It out for me in terms of AA bars. Show me that as well, because that will help you when I give you the next puzzle. I'm going to leave as takeaway, and depending on how tired you are, we'll finish NIM or do some other puzzles. Yep. Can you write that out? Yeah. Yeah. Very nice. Very nice. Okay. All right. So, yeah. Okay. So anybody who thinks they've got a handle on the first one is welcome to try the next one. Very nice. Write it out. Can you write out what that would be? Yeah. So, anybody who's solving the 3 version will have to come down and grab pins for themselves. And you're right here. I can give it to you. I'll leave an extra pin just in case. Okay. So, and there's no hurry. I mean, just take your time, solve what you want. I'm going to take a walk up here. That's all right. That's wonderful.
Okay, let me clear this. So this is clockwise,
Mm-hmm.
and then you cannot go anti-clockwise unless you go
Over.
again clockwise or
Oh,
anti-clockwise.
wonderful. Okay, so what have you done so far? So you did A, you did B. Can I have a B? Let's just write to B.
So I did A.
Then you did B.
Yeah, then I did B.
Then you did A bar.
Then I did A bar.
Okay, so now what would you need? So now if I remove the B, you're sorted. But if I remove the A, you're not. Okay? All right. How are we doing? Yeah, so if you need another pin, the box is right in the front. Go grab the box. Hey, don't grab the box, grab a pin. Somebody here have a mic? Yeah. Yep. Okay, so do it with the 3. Can you write it out? Apparently the stakes aren't high enough. Let's make this puzzle a little harder. So the paper I'm using, this is work by Eric Demain at MIT. It's a paper from the archives. And it's got some nice puzzles. It's actually got, okay. So for any of you, I have a feeling I'm not going to do the NIM. It's all right. If you want to talk to me about NIM, it's some beautiful mathematics, but I guess maybe let's finish this. Let's just compare it to Hackenbush in terms of what operations I have. Let's just talk about the mathematics. And I'll let you explore combinatorial game theory on your own. So let's just solve some part of this. And if anybody wants to talk NIM, I'm very happy to. So put your hand up and we can talk. Right? So with NIM, the question was, can you look at an arbitrary pile? Okay, so would you like me to finish that conversation on NIM, or should we just finish the picture hanging puzzles? I can give this to you as homework now that I can help you figure out how to solve them and then leave it as homework, right? And then we can quickly finish up the NIM. Does that sound like a good idea? So then let me walk you through how to solve just the basic 2. I'll send this to someone. I'll make sure you have this puzzle. Don't worry about it. Let me quickly do this then. Let me show you. Yeah, okay. So here is the solution to the first one. So if I did A inverse followed by B inverse, I would have nothing. It would not be hanging at all. What I want is to separate the A and the A bar with a B, and I want it to be symmetric. So imagine what would happen if I removed. Let's just ask this. Notationally, if I wrote out AB, okay, AB is just, that's AB. What happens if I pull out nail A? B will remain. So what you'll physically see is it's hanging off only this one. And in your notation, you just see the B, right? The same if I did it the other way, if I remove the A. Now here, right, so at least for me, the notation really helps me. So I don't know if some of you are good with the winding, that's great. But if not, so here what you're trying to do is you're trying to separate an operation with its inverse action by something, right? So that is how you're going to think about this. And I'm going to leave this as homework. So I will send this to you, but homework is to try to figure this one out. Okay, so this is what I'll leave you for afternoon. Yeah, so I'll send this to you. Yeah? Okay, so there's just a couple of, yeah. You want me to go back to the previous, sure. Okay, so there, I feel as if I left it half open. So I would like to just return to NIM and give you enough that you can go forth and read later. Okay? And again, the paper is just called Picture Hanging Puzzles. Google Eric Demain at MIT and you'll find the paper. It has solutions, so don't look until you solve them. Okay? So can I take the last 15 minutes to quickly wind up my NIM conversation? Yeah? So are we good with this slide? Can I move away? Yeah? Okay, so I'm going to... Okay. Okay, so someone asked me, how is... sorry, I'm trying to figure out how to make this full screen, just a second. Okay, someone asked me, so well, with Hackenbush, you said that if you chop from the bottom, everything falls down. With NIM, we had no such thing. You could take from anywhere, it didn't matter. How are these really the same game? There are two ways to do it. One is to think about the options that you have after a single play. Okay, so supposing, let's just take this simplest talk here. It's got three little piles, three little steps, three branches. Right? I can then cut it and make it two branches. I can cut it and make it one branch, or I can cut it and make it no branches. Those are the choices when I play on this stalk. Yeah? In the same way, when I play on this 3 token pile, I can either take away 1, 2, or 3. So one way of seeing it is if I were to draw out the tree, the options available to me, it would look the same. The other way to see it is if you and I play this one against the other, second player will always win. Okay, so there are two ways to see that these are the same game. So if I can figure the math of this out, I should be able to use it here. Again, what I want to do okay, so what I want to do, okay, this is where we started. 2 equal piles is the same as having just 2 single tokens, is the same as having 2 stalks of green Hackenbush. Who wins this? So now I've introduced a third pile. Till now we were working with just 2. Who wins this? Maybe the best way to do it is to play against me. So let's keep the picture hanging puzzle there. Let's do this here. Yeah, just to change it up. It's a 1, 2, and 3 piles of NIM. Someone play. Whoever wants to play, play. Can I have a volunteer from the back, please? Okay, so we're playing a 1, 2, 3 game of NIM. So there's 1, 2, and 3 in this pile. 3. Okay, 3 piles of NIM. And somebody up there tell me what to do. Okay. No, I'm not asking for a winning play right now. I'm just saying play anything. Do what you want, or you will respond. So somebody up there make a move. Yes. Can't convince anyone to play? Remove 2 from the third one, all right. You had a response? Okay. She's saying she'll remove. Okay, so if you were to remove 2 from here, there is a way to make it 2 equal piles. So 2 off of this is a risky move. All right. Now the same problem would happen if you removed 1 off of here. What would be the response? Well, I'd remove this and make 2 equal piles. So you can walk through the options and you will see. So what else could you do? You could take away all of this pile. Bad news, I'd make this a 1. Take just 1 from here. I'll take away this whole pile. Right? So pretty much walk through the options. Anything you do, this 2 is a 0. The question is, I don't want to have to keep asking. I don't even want to do this. So I'll leave this to you. I would like to walk over to a bunch of NIMS game, and I don't want to have to keep playing. I'd like to have some mathematics tell me what to do, right? How do I get to do this without actually playing through it? That is the question. Yeah.
Can we say that the total number of limbs, if that modulus 2 is equal to 0, that is if the total number of limbs are even, the second pair will always be?
Okay, so when you say the total number of NIMS, so yes, there is a good idea here. Now you're asking if it's the total number of tokens or the total number of tokens, if that is even. All right. Then you say that we will what, win or lose? Huh? Then the first place. So you're asking me, can I construct something? This is definitely true. I cannot have an odd number of tokens. And yes, so this is a true fact. So, but is being even enough? Okay, so that's the question. Right? So can I construct something that's even and yet winning? Yeah, okay, that I can do, right? So consider this game. Whoever walks over to this board is going to win. So being even by itself is not sufficient. It's necessary, not sufficient. Okay. But again, so what did we do with the 1, 2, 3? So what you're secretly doing, so any number can be written in base 2. Can everybody here write numbers in binary? Yes. Yeah, can anybody not? If you want me to, I can run through it. Can I assume that we can write out a binary representation of a number? Okay. So what we're going to do is we're going to write all these things in binary. Okay, I'll try motivating it a bit. All right, and then I'm going to try to use these as groupings. So I'm going to say for everything in the units place, anything in the, so for every position, I would like an even number of ones. Okay, so let's look at this again. This one is not a 0 because there is a way for someone to tweak it to a 0. Okay, I don't know, and I think at this point I'm trying to finish and I don't know if I'm succeeding. So again, please really talk to me. Tell me, so what I'm trying to say is if I write it out in binary, for every place value, I would like an even pair of numbers. When I look at this, I see that pink 1 on the left, I could remove it. And my claim is that this now is a 0. Okay? So I don't know if I did this way too fast. Yeah. Okay, so remember what it means to have a game that's winnable is that there is a way to bring it back to something that's a 0 and give it to your opponent. And the way to have something that is not a 0 is that there is a way for you to take it to 0. So from a, I don't know if that was a very complicated sentence. So somebody asked me something back there. I don't know if you guys are still doing picture hanging. No one's even looking up. So okay, I just wanted to do this because some people. Okay. So yeah, so we can, I don't want to do this. So let's just stop here. I just wanted to finish. And the reason NIM matters is that, let me skip through this quickly. Okay, so you can draw these wonderful pictures. This is from a Martin Gardner article with Conway, and this whole, what's called the Hackenbush homestead, consists of 5 NIM piles, and I can just analyze it in terms of NIM. Right? So what the reason that NIM matters is that any impartial game, so we've talked a little bit about impartial games, turns out they can all be turned into a NIM value. Okay? So a NIM value being how many, a single pile with a height of some number of tokens. That's a very, very strong statement. There is similar but very a little bit more complicated. You can turn, so partisan games are in some way related similarly to Hackenbush. Okay, so NIM and Hackenbush in some ways are very fundamental to combinatorial game theory because several other games can be turned into NIM and Hackenbush. So I just wanted to stop there. And whatever time we have left, we can go back to your picture hanging puzzles because I think that's where many minds are still. So, yes, if you want to talk about this, you're very welcome to come talk to me. I will put this back here. And I think we have maybe, I don't know how long we have. I don't know what time it is. So, okay, so here are the puzzles. If we have only a couple of minutes, I'll leave these puzzles here. Okay, so take your time, play, come talk to me. Yeah.
What is this field of maths dealing with games knowledge?
It's called combinatorial game.
Yeah.
If anyone has any question, do you want to discuss it? Nope. Yeah.
The other thing that I did not do is I brought a lot of stuff to show you. We're out of time, but Asa is going to, yeah, I'll go on, yeah. Yeah, so maybe Asa has some stuff to show. I'll answer questions. Go ahead.
So the games that we play today, essentially, like to the best of my knowledge and understanding, we can categorize into 2 categories. Where it's a 2-player game.
They were all 2-play games, except so the puzzle
picture
was a
hanging.
puzzle. This was a detour. This was
Okay.
just some abstract algebra for you. That's
Right.
all. Yeah.
Or something like NIM.
Yeah.
Either there's no differentiation between coins similar to red and blue. Otherwise, there is a differentiation saying red and blue. Right. So apart from games like that, another classification that we could have is a single-player game like Tower of Hanoi.
Okay, so those are typically puzzles, right? So, okay, actually Conway is most famous for something that's a 0-player game. So something called the game of life that sort of plays an automa. So it plays itself, right? So typically 1 player, so the question is, when you say a game, so if you're saying there's a set of rules and there's a way to win, why is a puzzle not a game, is your question?
No, like how, in an abstract manner, how exactly is it different from a very layman point of view, just a single-player game or a 2-player game, right? But
So
otherwise,
combinatorial game theory in general deals with two-player games. Okay, so all of the games we study are two-player, right? One-player games are the kinds of things we did here, like a puzzle. Tower of Hanoi is also a puzzle, right? So mathematically speaking, the structures are very different because, well, with a puzzle, there is a path to, there's an algorithm to solve it if it's solvable, right? Or if you can find the algorithm, maybe it's solvable, you don't know the algorithm. But with a game, uh, you're, uh, you're saying there too, could I not find an algorithm? But I think, okay, so there are something, yeah.
no, to the best of my knowledge, there is actually an algorithm to know, like, what is the quickest path that you can take to know solve the Tower of Hanoi.
Yeah, Tower of Hanoi, definitely, yes, yes.
So there's a game called The Goat and Tiger. Have you heard of it?
Yes.
Yeah, right. Yeah. So maybe that would also come under some category like this, right?
So it would be Partisan because it's two-player, but the tiger and the goat have different moves. So it is a partisan game. I don't know if any analysis has been done of it. So very often, games are not as simple as the ones I showed you. So sometimes it is possible to say something maybe I should have done. Okay, anyway, so there are games where you know that the first player can win, but you don't know how. So knowing that there is a strategy is very different from knowing what that strategy is. So even with the cows and the goats and the tiger, A, I don't know if there's any analysis. B, I don't know if there's any well-formed strategy. Like here, stuff like balance the piles, bring it to zero. It's very often not that easy to figure out what the strategy is. Okay, so I don't know if I answered your question.
No. I just wanted to know if you would still call that a partisan game, but it's more.
It is a
involves
partisan game.
even more complicated
Yes,
moves.
it's a partisan game that I don't necessarily know how I would analyze. It's not even if I knew. Okay, so I showed you this Pragrandi theorem. But what it says is I can turn anything into nim. Often I don't really know how. So there's something called a Grundy function that tells me how much of a nim pile. Maybe I should have. Maybe if you're interested, we'll do this some other time. But there are complicated looking things that I can just reduce to single pile of nim. Sometimes it's not that easy to know how to do this. Yes, it is a partisan game. I don't know if there's analysis.
Thank you.
Okay. I left the mic there, I think. Yeah, it should. Yeah, I think it's not. Yeah.
Can game theory also have applications in economics?
Okay. So the economics game theory is typically a different sort of game theory. It's more, so combinatorial game theory is completely deterministic, right? So there's trade-offs. People's choices have different outcomes. You have this playoff matrix and people make choices based on, so it's a different theory. So that game theory is not this game theory. This is combinatorial game theory. Yeah. Yeah, they can come. Sounds good.
Can you explain how converting those numbers to binary helps?
Yeah, okay, so that's an easy one. So, okay, so what I'm trying to do is that I know that if it was a winning game, I would have, okay, so with just two heaps, I know that I want it to be equal. Now I want to play off something with this, right, that would make the total 0, right? So now, so supposing I had piles that were not equal. Right, let me just go back to maybe something that's non-zero. All right. So so what I would like to do when I get it, eventually I'm going to try to get it down to something like that, right? That is just a unit 1 and a 1. Right? The extension to that. So what I'm trying to say is that no matter how many I put in here, I would be able to write it out in a binary representation, which would give me a path to responding to any gameplay you made. So supposing you were to do something, Let's just play this out and write out its mathematics. Let's just do 1, 2, 3 and write out what's going on, right? So let me just write this out as a 1 plus a 2. This is a 2 and this is a 1. Okay, I'm not going to try to do this very rigorously. I'm going to try to do it. Now, if I see this, so I as a second player, if I see this as groupings like this, let me try to, okay, so pick an action. So obvious actions, balancing the pile, you would be able to think of immediately because you've already proved that equal piles and equal piles are definitely paired up in any binary representation, right? So let's say take something that's a little bit more complicated, that is not equal, just two equal piles. What I'm trying to say here is that for any, so if you want to do something that, okay, we'll do something. Let's walk through what this means. So let's just write this out in binary, see what it means in terms of groupings, and try to work through a couple of steps. Maybe that will help. Yeah, I don't even really need the binary. Okay, go ahead, do something. You'll remove 2 from here. Okay, so my response, if you remove 2 from here, yeah, this is what I now see in front of me. So I will say that these two are already paired up in terms of parity. Okay, so the things I'm using are the fact that I can uniquely write something out in binary, and that if something has some parity, I can flip that parity back. These are the ideas that I'm trying to use here. So actually, maybe these 1, 2, 3s are a bit too easy. Actually, I thought this might be way too much, but yeah, I pulled out a couple of slides. Okay, so let's work with what we have. Sorry. So with this very simple example, the problem is that there's just so few things I can do that it's harder for me to see. Maybe how about this? If anybody wants to discuss this, come talk to me afterwards because it's easier if I can write. Okay, does anybody else have any? So there's some stuff that we brought along from the lab. It's got lots of interesting stuff. You're welcome to see it on your way. Yeah. Yeah. Sorry, I took away all the mics and hid them. Yeah.
So let's start. Join me in thanking the speaker. And we can discuss any questions later.